examples of designing combinational circuits now. We'll be starting with the simplest case, which is a half adder. So, like we said, the first step in designing any combinational circuit is to list the objective. Objective here is given two inputs, let's say X and Y. We need to develop a circuit that gives us two outputs, sum and carry. So this is our objective. The second step is identifying the number of inputs and outputs. So from the objective, it's clear that we have two inputs, X and Y, and two outputs, sum and carry. The third step is to draw a truth table of all possible combinations of inputs and outputs. So we have X, Y, sum and carry. So we'll first list out all the input combinations. They are 0, 0, 0, 1, 1, 0 and 1, 1. Now we list out the corresponding outputs. For 0 and 0, the sum is 0 and carry is 0. In case you're wondering how this happens, we're just performing normal binary addition. 0 and 1, sum 1, carry 0. 1, 0, again sum 1, carry 0. 1 and 1, the sum is 0 and the carry is 1. This is the third step. The fourth step now is to identify the relationship between the inputs and the outputs. In other words, we try to express each output in terms of the inputs. So we need to express S in terms of X and Y, and then C in terms of X and Y. And by in terms of, I mean that we're going to express S using X, Y and the basic logic gates AND, OR, NOT, NAND, NOR, XOR and so on. So we'll start with S first. So let's not look at the C right now. When you look at the truth table, the combinations of X, Y and the corresponding output S, it is clear that S takes a 0 when both X and Y have the same value, and S takes a 1 when the value of X is different from the value of Y. And we know from prior knowledge that this is exactly what an XOR gate does. So if both your inputs are the same, XOR returns a 0. If both your inputs are different from each other, XOR returns a 1. So we can say that X XOR Y is equal to S. Now we look at C. We see that C returns a 1 when both inputs are 1, and in all other cases C returns a 0. And this we know is exactly what our AND gate does. So C is nothing but X dot Y or X and Y. Now in this case we had only two inputs and the outputs were pretty straightforward. Just by looking at the combinations we were able to identify that this is an XOR gate and this is an AND gate. In case you have a more complicated truth table, let's say you had 3 or 4 inputs, or you weren't able to directly identify a relationship between X, Y and the outputs, you can use a K-map, or you can use the Quine-McCluskey method or any other method you're familiar with to derive this relationship. But anyhow, now that we have the relationships, the last step is to draw the truth table. To draw the logic diagram. So we have X, we have Y, we have our circuit, and we have our outputs, sum and carry. So we just saw that S is equal to X XOR Y. So we take X, we take Y, we connect both using an XOR gate, and this is our sum S. Again, carry we just derived is X dot Y. So again we take from the same X and the same Y, we connect both by an AND gate, we get our carry. It is important that you make this connection again from the same XY and not a different XY here, because we're giving the same xy. We don't give two different pairs of xy. So if you made a separate x here, y here and connected that, it would mean that is a different input and this is a different input. But we know that these two coexist for the same input combination. So this is how the circuit is drawn. So that is an overview of your half adder.